So as a bit of a review, kind of basic properties of, in this case, we're going to be less general. We're going to say straight our parent function is y is equal to 2 to the x. Key points are 0, 1. That's going to be my y-intercept before any transformations. And then if I plug in 1 into my equation, I'll get 2. And if I plug in 2, I will get 4. And so those are going to be our 3 key points when we're going through this transformations. The other kind of parent function is if b is between 0 and 1, and we typically talk about that with 1/2. And the key points for that, I don't think we'll kind of see an example in this section, but the key points for that are going to be, would be, again, 0, 1, and then 1 and 1/2, and 2 and 1/4. The reason that we don't really talk about it much in this section is because it's fractions, and fractions can cause a bit of a headache, but it's perfectly fine. The concepts apply exactly the same. You just have to be careful when you're adding and subtracting. So we talked about it in the very general case, y is equal to a times b to the x, and your horizontal asymptote is y is equal to 0. That is true from both of these parent functions as well. The same horizontal asymptote, same domain, negative infinity to infinity, and the same range that we saw in the last lecture, 0 to infinity. So we got to keep all of that in mind when we're kind of maybe ask questions after our transformations of what's our new domain or what's our range. Or specifically, we like to, in this class, talk about what happened to the horizontal asymptote. So keep those 3 things in mind. X-intercept is none, because we have that horizontal asymptote with y is equal to 0. Y-intercept is 0, comma a, or when we were talking about y is equal to 2 to the x, 0, comma 1. And we don't really talk about that this much in this section. That's why I'm actually not going to fix the error on this one. The graph is going to be increasing if b is greater than 1, and it's going to be decreasing if b is between 0 and 1. So it's that, is it a exponential growth? B is greater than 1. Yes, increasing. Is it exponential decay? Between 0 and 1, then it's decreasing like the graph on the right. Now, evaluating an exponential. You don't really have to know a whole lot from the section to answer this first question. When you're evaluating anything, you say, okay, what function am I talking about? I'm talking about my f of x function. I'm going to put in 5 for whatever my input is. So in this case, it's x. So to evaluate this, I just plug in 5 for the x in the power. And then 5 minus 3 is 2. 2 squared is 4. So then, skip the line. 3 times 4 gets you 12. Well, I just defined it. A logarithm is the inverse of an exponential. So might not be super comfortable with the term inverse, but one of the most famous inverses, or at least inverse relationships, is addition and subtraction. And that's because when you are solving an addition problem or solving something like x plus 2 is equal to 1, well, you subtract from both sides. Another pretty famous inverse pair is multiplication and division. So that's the entire reason logarithms were quote unquote invented or exist, is that when you have an exponential function and you want to solve it or you want to undo something that has a power, well, you use a logarithm to undo that. So that's the connection. And so we're going to start with a very important part of the process, which is just translations. So in this case, I have b to the y is equal to x. Well, if I wanted to solve for y, if I wanted to get y by itself, I would take the log base b from both sides. And so that would cancel out the b on the left side, and now I would be left with log base b of x. I say base, that's the thing right next to the log. So anytime you hear me say log base something, I'm talking about the tiny letter or number that is to the bottom right of the logarithm. And vice versa. Like if I have a logarithm, y is equal to log base b of x, and I want to solve for x, well, to undo my logarithm, I take an exponential. So I would take b to the log base b of x on the right side. That would cancel my log, and I would be left with b to the y is equal to x on the left side. So to see this in practice, quick note. The domain of logs is 0 to infinity, and the range of logs is negative infinity to infinity. And if you're really good at kind of putting pieces of the puzzle together, you might notice, okay, well, logs in exponentials are inverses of each other, well, the domain and the range of a log and an exponential are flipped. So that's kind of where those come from. We'll see that more when we get to graphing, but that's kind of just to hammer home this relationship a little bit more. Now for starters, we're not even going to solve. We just want to be able to translate, because that is the first piece of the puzzle. I said puzzle a lot. That is the first piece of the process when we are solving for logarithms or exponentials or anything like that. So before we get into deep with anything like that, we want to make sure we understand how to get from one to the other. And I will use this term a lot in the next couple of sections. I'll say I'm translating this to that or that to this. This is what I'm talking about. So I have a logarithm. I want to translate it to an exponential. So I have log base b of 3 is equal to b. Well, I look up at my translation on the top of this slide, and to get a logarithm to an exponential, I swing that little number, that tiny number, over to the other side. And so in this case, I would have 3 to the b, and then I'm solving for x. And here I have log base d of 4 is equal to 5. I will move my d to the other side. My right side will become d to the 5th, and I'm left with just a 4 on the other side. We'll see it once more. And in this case, this is actually solving what a log would be like. But again, we're not focusing on that, just the translations. So I have log base 3 of 9 is equal to 2. I'm going to take that tiny 3, I'm going to move it to the other side, so I get 9 is equal to 3 squared. I'm undoing those logarithms. Now to go the other way. I have x is equal to 3 to the b, and just to kind of mention it, I'm sure I've mentioned it before, an exponential, we call that bottom part base as well. So when I say log base b of x, I should also be saying, in this case, the base of 3 to the b. It's just a little bit redundant, seems kind of clunky, but that is what we call that 3. So in this case, the base of my exponential is 3, so I'm going to move that to the other side, and I'm going to have a log base b, or a log base 3 of x, and now my b is by itself. So I'm kind of isolating b. Here I'm going to isolate my x. Okay, well the base of that exponential is 2, so I'm going to move that to the other side. That's going to become the base of my log. So I will have log base 2 of 8 is equal to x. See it again, I have y to the x is equal to 5, and I kind of put this example out there to emphasize as well where things are showing up aren't super important, as opposed to like the left side of the equal sign or the right side of the equal sign. It's more, what am I translating to? So in this case, I'm going to take an exponential, put it into a logarithm. The base is y, so I'm going to move it to the right side. It'll be log base y of 5, and then I'll have x left. Now I have 10 to the third. Yep, that's certainly 1,000 if I throw it in my calculator. But if I want to translate it to a logarithm, I move the base of 10 over to the other side, and the left side becomes the 3. It becomes that power. So notice how the power in this case is kind of just dropping down on the side, and then the base is moved to the other side with the logarithm. Now, something worth mentioning. There are two very special, important logarithms. The first one is log base 10. We see that a lot when we're talking about scientific notation, for example. You see 10 to the certain power all the time in chemistry and stuff like that. And since we see it so often, we just call it, I believe, the standard log, or we just don't write whatever the base is. So if you have a graphing calculator on you, you might be looking around it to see where the logarithms are. And if it's not a fancy new calculator, there's probably a button that says log, and there's probably a button that says ln. So the log button is taking the log of base 10, so it's that translation. And so if you see just a logarithm when you're working through WebWorks, because they definitely like to do this a lot, or I'm talking about it on the lecture, and you don't see a base, assume that base is 10. Now, the second log that is super important revolves around that concept that we brought up last lecture, is this e guy. So e seems like it's a variable because it's a letter, but it's actually a very, very important number, and we use him so often that instead of writing him out, we just call him E. I think it's 2.71312, I want to say. And so, again, not really super important to this application. Really, we want to try and translate this question. So I have e to the x is equal to 7. To translate it, my x drops down. My e becomes the base of my log on my right side, and it will be log base e of 7. Now I mentioned in part D, oh, these are both D. I mentioned in the log base 10 question there are two very important logs that are so special we give them their own names. Log base 10 is one of them, and then log base E is the other one. And so we call log base E the natural log, or ln. So when you see ln, you might think, oh, we're not dealing with logs anymore. No, it is a log. In fact, it's log base E if you really want to write it out. But when you get kind of beyond this course, especially in calculus, people love talking about natural log ln. So just kind of get used to that notation as opposed to log base E. The log base 10 is slightly less important. You could be justified in asking, oh, what is the base of that? Where if there is no base, where ln is just so standard, it's important to kind of know the relationship in between the two. And in fact, at this point on, I would recommend not writing log base E. Just know that that is the same thing as ln. Also, I don't know if I've used those double arrows before. That's a cute math symbol that means they're the same thing. They're equivalent. So if you ever see that in a math book or see it when I'm going through something, that means I'm going to be able to use them interchangeably. And then I mentioned it's called the natural logarithm. Now, to kind of really hammer home the connection between the two. When we talked about an exponential, the exponential domain of an exponential is always negative infinity to infinity. The range of an exponential, unless it's been transformed, is 0 to infinity. Well, a logarithm is you just flip those. So the domain in this case will be 0 to infinity, and the range will now become negative infinity to infinity. So if we're trying to find the domain of a logarithm, we kind of use a process. So when we talked about domain a while back, I mentioned at the time that there's three types of things we'll see in this course. There is a fraction, and there's a process to find the domain of a fraction. There is square roots or roots, and there's a process to find the domain when given a square root. And then there was, quote unquote, pretty much everything else, where this is the time that this breaks that pretty much everything else. That's not to say forget that whole process, because it still holds entirely true, but we just have to add kind of one little additional thing to the everything else section. And so that's logarithms. Logarithms do have their own domain. When we get into solving logarithms, we need to be checking our answers again, because we can have extraneous solutions. But as far as the process goes, it's the exact same process as a square root. It's just instead of greater than or equal to 0, it's just greater than 0. So that's why I'm saying the method still works, the three-type breakdown still works. It's just when you see a logarithm, think, okay, it's square root, and now it's just greater than 0 versus greater than or equal to 0. So to see exactly what that means, we have this logarithm. We take whatever is inside. I don't care what the base is. I take whatever is inside, x minus 4. I'm going to set it greater than 0. And then I just go ahead and solve. Add 4 to both sides. So my domain is 4 to infinity. Now, as far as kind of just a very brief introduction of logarithms, the graph on the left is not a logarithm at all. It's an exponential. We've seen that before. What a logarithm is, and this is how you graph any inverse. I've talked about this before, I believe. Yeah. Is we draw a y is equal to x line, kind of a dotted line that's not even really there, and we flip it over that line. So the graph on the right, again, the top thing is still my exponential, but the bottom thing in blue or maybe purple, depending on how you look at it, that is my logarithm, and that's because it's an inverse. And if you look at that graph, oh, okay, yeah, the domain is 0 to infinity, the range is negative infinity to infinity, and we're going to talk about some other properties. But that's where this comes from. If you had never seen a logarithm before, you wouldn't really even need to know specifically what a graph looks like, because there is this relationship, and that's where the shape is kind of coming from. Okay, yeah. And so when we talked about exponentials, the parent function standardly, but not always, or typically, was y is equal to 2 to the x. And in this case, unless otherwise specified, generally we talk about the parent function of a logarithm to be log base 2 of x. And so that's what the blue graph is.